Welcome to our session, Scalable and Manageable, a deep dive into GKE networking best practices. Because we all know how perhaps unnecessarily complicated networking can be, we kept the title of the session long and dry instead of making it brief and simple. Hi, my name is Bowei. I'm an engineer on GKE networking.
Hi, my name is Mahesh Narayanan, and I'm a product manager in GKE as well. So the format of this session is going to be a bit different. Bowei and I get on a lot of calls with customers talking about their issues, design and architectural considerations, product overview, so on and so forth. So what we have done is we have encapsulated the customer questions, and we're going to try to come up with the solutions and recommendations and best practices that addresses those questions. The idea or the aim of this session is to look under the hood at the engine of GKE and look at the different advanced cluster management options and fine-tune this engine. Some housekeeping. If you have any questions about this session, please go to Dory Q&A. It's an internal tool that we have used quite a lot in Google, and it gives an opportunity for everybody to ask questions. If you like a question, please upvote it so that it has a higher probability of it being asked. OK, so you start off dabbling with GKE, our powerful orchestrator and cluster management service. As you spend more time, your confidence grows, your skill set grows. You start building more and more mission-critical applications, and migrating them to GKE. Clusters start seeing more and more traffic. Soon enough, your cluster size gradually starts growing to a point where you start running into scalability and manageability issues. These issues can often be avoided by following best practices and guidelines from day one. So that's the crux of this session. We often hear from our customers that they run into routes quota. So as somebody approving quota requests, we see a lot of increase in quota requirement because of GKE route-based clusters. Laying out your VPC is the most important facet of deploying GKE clusters. One of the key binary decisions that needs to be made is whether you're going to use routes-based cluster or VPC native clusters. Now, what are these? Kubernetes mandates pod-to-pod connectivity. And when a pod is talking to another pod in a node, it uses the cluster, the bridge interface to make that happen. But across nodes, you need some support from networking to make that happen, both overlay and underlay. So GKE started off with routes-based cluster. And what it did was it used static routes. So it used a static route. The nodes used a static route and announced itself as a next hop to all the pods that it hosts. It's fine for a small cluster, but as your cluster size grows, your routes quota also increase, your requirements also increase. So in anticipation of growing clusters, what it did was we came up with VPC native clusters, which under the hood uses alias IP. Which basically is using secondary IP on its interface, on a NIC. Now, VPC native mode is enabled by default. And the biggest advantage over routes-based cluster is that it doesn't require that many routes quota. Apart from scaling, as the name suggests, it also natively integrates with VPC Fabric, allowing other functionalities and features like shared VPC, private clusters, flexible IP management, ARP snooping checks, so on and so forth. So let's talk about IP management. Most often, the deployments are blocked not because of some fancy new feature, but because of lack of contiguous IPs. I've been on many calls with customers where they have a spreadsheet with IP inventory, and they're trying to match the size of the scale of their cluster with IPs. So let's look at IP management from GKE. What are some of the resources that use these IPs? And what are some of the options to reduce IP utilization on GKE? So Kubernetes itself uses IPs liberally. The different resources. So before we get into IP optimization, let's look at what are the different resources that uses IP. There are three resources that require IPs: your pods, your nodes, and your services. So the nodes use the primary range of a subnet. The pods use a secondary range of a subnet. And the service also uses a secondary range of a subnet. The service and the pod secondary range need to be different. We don't allow you to use the same secondary range. Now, what are the advantages of having separate ranges for all these resources? There are a few advantages. The first is, it's more intuitive if you have any security policies, and from a tracking perspective, it's much easier to have separate ranges. You can grow each resource independently. And lastly, if you want to apply any security policy based on CIDRs, it's also easier. So VPC native provides two modes of IP allocation to resources. One is the auto IP mode, where we take care of everything. GKE's responsibility to allocate IPs to the different resources, and it takes care of ensuring there is no IP overlap. The drawback is that we assume certain cluster size. We assume a moderate cluster size and end up taking an IP block based on that assumption. However, if you are building a smaller cluster, you want finer grain control, you can use a custom IP option where you can decide the subnet, you can decide the range, and reduce your overall IP utilization. One other way of reducing your IP utilization is using the primary range and the secondary range for pods across different clusters. Right? We don't allow the secondary range for services to be shared across different clusters, but for the pod primary and for the node for the pod secondary and for the node primary, you can share it across different clusters. And last but not the least, there is a new knob that we added called max pods per node. So let's talk about that. This feature just went into beta. So to understand the crux of this feature, let's define pod density as the number of pods running per node. So we talked about how you define a pod cluster or a pod range which allocates IPs to all the pods in your cluster. But since the node is actually running those pods, the nodes need to carve out a specific or a smaller CIDR from this overall cluster, right? So with pod density-based config, we have kind of opened up this option to the customer. You decide how many pods you're going to run per node, and thereby the node carves out that many IPs from the bigger block. So as an example, let's say you give a /20 for all your pods in a cluster, and you're planning to run 8 pods per node. We take a /28 from that overall /20. So your /20 exhausts more slowly. You might ask, why are we taking a /28 if it is only 8 clusters and not /29? That's because we take double the amount of IPs for avoiding issues like IP reallocation when the node goes up and down. So this is an example of how you can create a smaller cluster. Nodes per cluster, 12, so you take a /28 for that. Services, you're planning to run 20 services on this cluster, so you take a /27 for that. And the cluster pod range that you define is a /24. Now, you define, as we talked about pods per node, you say every node is going to have 8 pods per node, so that's /28, and there are 16 /28s. So you are good from all the different scaling perspective, right? You have /28, which gives you 16 IPs, 32 IPs for services, and 16 /28, so you're good to go here. Right? So switching tracks from container native networking and from IP management, let's look at network security. The summary of the ask is that a customer wants a completely isolated cluster. Right? They want to access Google services privately. They might have few workloads which needs to access third-party APIs, and for that they need a deterministic IP. And they want a deterministic IP because the third-party vendor has a whitelist blacklist policy which requires a deterministic IP. Right? So how do you meet this requirement? You run something called GKE private clusters. And in GKE private clusters, we take away any public IP, and it's basically isolated from the internet. Now, I want to clarify that when I say it's isolated from the internet, you can still configure an ingress or a service type load balancer and allow ingress incoming traffic to the cluster from the internet. Okay? So based on the slide, there are 3 steps to take to isolate your cluster. First is choosing the cluster type. We have primarily a public or a private cluster. If depending upon your requirement, you can choose between the two. You can expose the cluster master And cluster master is basically where we host the K8s API server, the HCE, and scheduler as well. So that is in your control as to how you're going to expose that. And then whitelisting access to that cluster master. So network security is a shared responsibility in that it's our responsibility to secure the managed element, but it's your responsibility or the user's responsibility to ensure that they are using the right option to kind of lock down the cluster master as well as the worker nodes. Now, in a private cluster, as I was talking about, there's only RFC 1918 addresses. There's no public IP, right? And this, by default, prevents it from talking to the internet. In private clusters, we turn on private Google access by default, which means you can access any of the star.google APIs privately. But if you have a requirement for certain workloads to go out, you can also integrate it with CloudNAT. So you can provision a CloudNAT and integrate GKE cluster with the CloudNAT functionality. Second step is exposing the cluster master endpoint. So here you have two options. You can create a private endpoint, which gives a private IP to the cluster master. And this can be used to access from on-prem. If you have a kubectl client over there, you can use that private endpoint to access from on-prem. You can also expose a public endpoint, and this is especially useful for road warrior use cases where you have a remote worker who wants to access your cluster master. However, you expose a public endpoint, it's also accessible to any untrusted actor as well. So what we do is we give you whitelisting, blacklisting, a whitelisting facility through authorized network with which you can decide, you can allow the trusted and disallow the untrusted. So just to summarize, I want to talk more about the authorized network, but before that, let me summarize what we have discussed thus far. So there is public endpoint and private endpoint for accessing the cluster master. And in public clusters, you get only a public endpoint. In private clusters, you can have, by default, it gives you a private endpoint. And it also can extend a public endpoint to you for road warrior use cases. Whitelisting through the authorized network that I was talking about, there is a default behavior, and there is there's another behavior when you enable it. I'm not going to go through the table, but there is a lot of flexibility in terms of different permutation and combinations that we support to meet your security and compliance requirements. DNS scaling. So kubedns is a service that is used for intra-cluster within the cluster name resolution, right? kubedns deployment logic takes into account the size of the cluster, but it doesn't take into account the number of requests, DNS requests that might be going across, right? So the kubedns lookup takes up contract entries. So if you have a small cluster, so you might have a use case where it's a small enough cluster, but a very chatty application which is exhausting your contract table, which can lead to issues. So what you can do is use DNS autoscaler to set up to modify the number of DNS backends that will run. And this, by default, the equation takes into account the number of nodes and number of total cores across your cluster. So what you can do is you can override that. If you say that, hey, this is a small cluster, I'm not satisfied with the number of default backends I'm getting, you can increase the min number of backends or DNS replicas that you want to run. As an example, let's say you have 10 nodes, 8 cores per node, so total 80 cores running in the cluster. So by default, you are getting, because of the function, the logic, you are getting 2 DNS replicas. But because of the min setting that you had, you bumped it up to 5, right? So that's another way you can get over the contract issues. And as you may know, there are some applications that are heavy users of DNS. Node.js is an example. If you have control over the name that they resolve to, you can avoid search path extensions. One of them is through the application itself that is pointed out in the top, and the other one is through making changes to the pod spec. So with that, I'll hand it over to Bowei.
So let's now talk about running services at scale. So at first, you may start off using an in-cluster-based ingress controller, which just uses an ordinary proxy server and uses service-type load balancers to expose it to the internet. This is really familiar for a lot of us. It's just the standard proxy that you would run on your laptop, and then you would expose your application to the internet using service-type load balancer. However, when your application scales up, you will really want to use the Google Ingress implementation in Kubernetes engine. This is a container-native ingress that's globally scalable, low latency, distributed proxy layer, and it has lots of built-in features like caching, authentication, DDoS protection. You won't have to fiddle with figuring out how many instances of your proxy to scale to or how to worry about absorbing an attack. But in addition to this, what are some best practices around using services? So first, let's talk about seamless services. Production services often require software updates and upgrades, and ideally without disrupting to your users. Kubernetes Engine gives you a bunch of knobs to ensure your services are updated without impact. But how these pieces interact can be subtle. Let's walk through each of these pieces to understand how they fit together to ensure that your users won't see network hiccups as you scale and update your applications. OK, let's talk about a pod's lifecycle, particularly focusing how the pod lifecycle relates to services. So there are three basic states that govern how your pod interacts with your services. First, there is liveness. This determines whether or not your pod is up. For instance, if your pod fails its liveness check, it will be restarted. The second bit is readiness. This determines whether or not your pod is fully booted up and healthy and ready to serve traffic. For instance, this is used by workload managers, such as a deployment resource, to see if it's OK to continue updating your application. Finally, there are health checks. These come from the load balancer infrastructure itself and are end-to-end checks of both network and application health. OK, so let's walk through what a pod lifecycle looks like and how to ensure no service disruption. So this diagram depicts a timeline of the pod status. We have a line for each of the three states: liveness, readiness, and health check. First, we start the pod. It should be alive. If it wasn't alive, it would be dead. So then that would be the end of the story. OK, so next comes health check and readiness. Now, these can go green independent of each other. But when they go green, your pod will start seeing traffic. The load balancer will be sending traffic to your pod. Now your pod is running for a while, and you do an update of your deployment. Here is when your pod is going to be terminated. What the system will do is send your pod a SIG term. If you don't handle it, your pod simply ends here. However, as you can see, it's still serving some traffic. So you will drop some requests on the ground. If you do handle it, then what you should do is start failing the health check and readiness. What this will do is tell the load balancer to start draining the traffic off of the pod. Finally, after a fixed amount of time, Kubernetes will finally send the SIG kill, which will kill your application for good. So how do we have seamless services? Let's recap. So the most important thing is when Kubernetes sends you a SIG term, you have to start draining your application. Requests may still be in flight to your application, but no new ones will arrive there. Now, the way to tell the load balancer that this is happening is to fail the health checks and the readiness probe. Second thing is, after termination grace period seconds, your pod will be killed with SIG kill. Now, if you don't set the setting, its default is 30 seconds. But if your application takes longer than 30 seconds to service the last few requests, make sure you adjust the setting. Finally, setting these grace periods may impact how fast a deployment can update. So make sure you tune your deployment max surge and max unavailable parameters to take into account for this. For instance, if you can only tolerate having one pod being upgraded at a time, then your upgrade of your whole deployment will proceed only one pod at a time, and we'll have to wait for the grace period. Now that we talked about, oh, yes, and one more thing. If you have infrastructure that needs to be integrated into your pod lifecycle that does not necessarily come from your pod itself. For example, you have to, as part of pod startup, talk to a network load balancer, program the load balancer, and then inform the pod about the load balancer's condition. There's a feature called pod readiness gates, which lets you add these custom conditions from outside of Kubernetes back into your pod lifecycle. So how does this work? Well, here's your pod lifecycle, and we see that the readiness gates actually slot in the readiness condition at the front. So one concern that you have when you scale your backends to thousands is that of load balance. In the ideal case, you want your request traffic to be evenly distributed across your backends. So here's a situation that actually has come up a few times that we've seen is suppose I have a load balancer with a backend, or two backends in this case, and traffic is flowing. And I have traffic to my backends, and now I want to scale up my application. Now I have 4 backends. And we see that when we send traffic to these backends, it's actually preferentially going to the older backends. So why is this? And is random shuffle not actually random? So we know that Kubernetes and the load balancer uniformly, randomly sends requests across all the backends. So what's going on? To answer this question, let's zoom in and see what's happening. Let's take a deeper look to see what the infrastructure looks like. So at the top, we have Google Cloud Load Balancer and Kube Proxy. Now, requests are balanced to the nodes. In fact, they're balanced evenly. But the Kube Proxy then balances connections to the pods. So if you see here, we've scaled up. We added a few more connections. But when the requests come in, traffic is actually evenly balanced to the VMs. But, and this is especially true for newer protocols like HTTP2, there is significant connection reuse. And requests will actually likely go to older backends, causing an imbalance of requests. So how do we fix this? So really, there's a disconnect between connections and requests. So what to do? Well, there's 2 options. One of them is complex. So you can modify the backend to return headers indicating that connections should not be reused. Basically, the crust of it is don't use the connections too long. And if you do this sufficiently often, you will eventually get a uniform distribution of connections. However, there's an easier answer, which is to use container native load balancing. So with network endpoint groups in Google Cloud Load Balancer, the load balancer sees every pod backend as an independent entity. In this case, even you have a very skewed set of connections from the load balancer to the backend, the load balancer can look at that, look at the requests, and send it to the least utilized backend. And finally, one final thing is this problem really can crop up anytime you use an L4 service type with connections, and you have this kind of aggressive connection reuse. So this is one thing to watch for. OK, so in addition, and this is container native load balancing, you'll have a nice even distribution of requests. Now, in addition to accurate load balancing, when your LB knows about your backends directly, you will have accurate health checks. You won't have the double hop through Kube Proxy. And you'll have much, much better visibility and debugging. For example, when you go dump your traffic, you'll see the traffic go directly from the load balancer to your backend, nothing in between, no tracing needed through Kube Proxy or IP tables. Now, finally, in terms of scalable services, we should talk about failures. So the common way to think about failures is to think about failure domains. And in this case, we have to think both about our data and control plane. What this means is that if you have a single or maybe multiple faults, they won't cause disruptions to your users. Now, we could have failures of, for example, a VM. And if you have a correlated failure where all of your pods of your application are scheduled on the same VM, then you may have an outage. One way to avoid this is to use scheduling constraints, such as pod anti-affinity, to distribute your pods across the nodes in your cluster. Another failure domain you want to consider is a zonal failure. For example, in this case, US West 1A has gone down. To handle zonal failures, you probably should do 2 things. One, for your data plane, you should have node pools that are spread across multiple zones. And for your control plane, you will want to use regional clusters. Regional clusters gives you a distributed control plane across multiple zones for your API servers. Finally, we forgot about one thing, which is the config plane. So not only do you have the data plane and the control plane, but you should be careful that you can't make that one edit to a config. I know we all did it. And it takes down your global network. So ideally, you should have separation here as well. Separate your clusters by namespaces or by clusters for staging and production. Make sure you stage a copy of Kubernetes resources, test, and then commit the real thing. So that's the advantage of Kubernetes, is this declarative model that can be checked in, and you can run CI/CD on your YAMLs. In addition to thinking about it at the sort of cluster namespace level, You can also think about it at the services level. For example, if you have a service, you can use the Kubernetes selectors to merge multiple deployments together. So you don't have that one golden deployment that you can edit and put all your eggs in that basket. OK, so we've seen a couple of best practices. And now let's go over what they actually look like on Kubernetes engine. So first, we're creating a cluster. And as we recall, we want multiple failure domains. So we create a regional cluster. Next, we know that we want IP flexibility and all the access to all the features. So we make sure it's a VPC native cluster. And also, we have sort of know about how our workload scales with respect to IPs. So we can set a smaller maximum pods per node to kind of save on IP address usage. Finally, we use HTTP load balancing, which is the Google ingress. And we want a private cluster because we want it to be secure. And finally, we put ACLs using master authorized networks. So let's see what this looks like when we make the cluster. Can we switch? OK, so we have this cluster, right? And we see that it has 3 nodes. In fact, all of these 3 nodes run across the distributed control plane, which is in a region, US West 1. And in fact, when we look at our nodes, we see that they use less space than the default, right? Because we have scaled our cluster to be smaller IPs per node, so we can fit more nodes into our network. And also, from a failure domain perspective, we see that it's actually sharded across all of US 1. So if one of these zonal shards goes down, we still are up. Now let's look at the container native load balancer. So this is a standard definition for an application with a load balancer. We have the deployment, which I was speaking about earlier, with how you get your workload in the cluster. Then we have a service. And the service is where we say we want to use network endpoint groups, which is the container native load balancing. And finally, we expose the application using ingress here. Now, let's take a look at what this load balancer looks like. So here we have the load balancer that was created from that snippet of configuration. And you'll see that it's split over 3 zones, right? We have 3 zones for reliability. And in fact, when we click into the zone, we'll see that all of my backends are my pods. So I have very accurate health checks from the infrastructure telling me whether that infrastructure, the load balancer to that particular pod directly is healthy or not. All right, so in summary, what were some of the best practices for using GKE in regards to networking? Well, first, you should sit down and understand your cluster IP space and plan for future growth. And also use VPC native clusters to get the maximum flexibility in terms of IP space planning. The second thing is make sure you understand what your security requirements are, but really you should be using private cluster and master authorized networks to secure your clusters. Also, tune your pod lifecycle to avoid service disruption. So, handle SIG term, make sure you respond correctly to the readiness and health checks. Use container native load balancing for the best performance and visibility of your traffic. And finally, understand and plan for failures on the 3 planes: data, control, and config. And your feedback is greatly appreciated, so please fill out the survey app at the end.
And you can also submit your questions through Dory.